Thanks. So I'll be talking a little bit about the evolution or the story of Plonky3. And I wanted to start first by talking a bit about the different fields that we looked at, since they're so important. So this table on the right here, this is actually from the very first GitHub issue of Plonky2. And back then, we were looking at different 64-bit fields. We knew we wanted to do something with small fields, and there wasn't much work on using this like 64-bit fields, so we were investigating different options, including what became known as the Goldilocks field. And these 64-bit fields make a lot of sense for scalar CPU code, because 64 bits is the largest integer type that most CPUs support. But in a more optimized prover, really we want to be vectorizing most of the prover work. And vector instructions usually work with 32-bit math. So we're looking, in Plonky3, we're looking at 32-bit fields. And what's the best 32-bit field? It's kind of an easy choice. There happens to be a 31-bit Mersenne prime, and Mersenne primes just have the best the fastest modular reduction possible. So we see this as sort of the end game of CPU-based provers, this 31-bit Mersenne field. But it doesn't have the factors of 2 that we normally expect in ZK finite fields. So how do we support this prime that doesn't have these powers of 2? So why do we need all of these powers of 2 in a finite field? There are basically 2 reasons. One is that most ZK protocols involve FFTs, and if we're doing a Fry-based prover, then Fry usually expects powers of 2 as well. But really, both are more general than that. So if we look at the Cooley 2-key algorithm, fundamentally it works with any composite n, and doesn't have to be a power of 2. It just needs to be divisible into 2 components. And similarly with Fry, if we're doing radix 2 folds, then we need powers of 2. But Fry is also more general than that. We can use other folding factors, and we could even have like a large prime in there that just becomes the final polynomial at the end of Fry. And the Mersenne 31 prime has a somewhat smooth multiplicative subgroup. So it only has a single power of 2, but it has a few powers of 3, and 7, 11, and so forth. So we could do something like a mixed radix FFT using these different factors rather than just factors of 2. And we could similarly do mixed radix Fry. We explored this a lot, but there are some caveats here. So if we're not using complex roots, but assuming that we're using real roots of unity, then radix 2 FFTs are still the most efficient, and we are giving up something by moving to mixed radix FFTs. Also, if we have to use some of these larger factors, like this factor of 331, then we have to use kind of non-standard FFT algorithms like raders, and these involve convolutions, and we still get a n log n FFT, but it ends up being more expensive. So we were looking for a different way to support Mersenne fields, and another option is to use a completely different ZK protocol, something like the tensor PCS, which generalizes the Ligero scheme. And this is often instantiated by Breakdown or Orion. It's instantiated using the particular linear code that's based on expanders. And these expander codes are really nice because they support linear time encoding, and they support essentially arbitrary fields. We had to do a slightly different analysis of the expansion properties, but we can support fields like Mersenne 31. And the prover speed is also potentially very good. It's very configurable because we don't have to use a particular rate like 1/2. We can basically use whatever rate we want, which could be very high if we want to maximize prover speed. The caveat here, though, is that we just don't get very good succinctness from these schemes. They have this square root of n proof size and verifier cost. So the next step for us was coming back to Reed-Solomon codes, and we kept thinking about how the Mersenne field doesn't have enough powers of 2, but the complex extension does. The complex extension has 32 factors of 2, which is plenty. So what we could do is do Reed-Solomon encoding using complex roots of unity. That would work, but that would give us this low-degree extension in the end, which is complex instead of real. And that's not great because then we have to commit to these complex values, and we're basically doubling our commitment work. Luckily, our teammate Ulrich noticed that although this output is complex, really these complex values all lie on the same degree 1 linear subspace of the complex plane. So we don't really have to commit to complex values. We can actually compress them into real values and commit to those, and then the verifier can later decompress the committed values. So this makes commitment very fast, but there is still a caveat here, which is that we still, when we go to do the 0 check, where we're computing this quotient and evaluating constraints over the LDE values, now these LDE values are complex, so the inputs to our constraints are now complex. So commitment is fast, but constraint evaluation is slower. And finally, we did a research collaboration with Starkware, which led to a better solution. And this is Circle Starks. And the idea here is similar to ECFFT and ECFRI, essentially generalizing FRI to support these other algebraic geometry codes, in particular with this circle code based on the same unit circle group as before. And this gives us a Stark that's very similar in performance to a traditional univariate Stark. There are a few selector polynomials that are a bit different, but it's essentially the same process of low-degree extensions and evaluating a quotient argument now with real inputs. So this gets us essentially the best of both worlds. We can support Mersenne 31 without any of those caveats mentioned earlier. Besides support for Mersenne fields, Plonky3 has a couple other interesting features I want to mention. One is that it has more powerful batching. So in Plonky2, we would have these ZK VMs with multiple coprocessors, and each coprocessor gets a Stark that then get connected together through lookups. And in Plonky2, we would have these multiple traces, and each trace would get its own Merkle tree and its own FRI protocol, which isn't the best for succinctness because the overall ZKVM proof ends up needing several Merkle witnesses for these different coprocessors and several FRI verifiers. In Plonky3, we batch them all together, so we have a single Merkle tree even for multiple matrices of different lengths, and we roll them all into a single FRI instance. So we start with the longest matrix. That becomes the initial input to FRI, and as we go through the commit phase of FRI, partway through that commit phase, we mix in any smaller matrices. Plonky3 also supports symbolic evaluation, so we can do things like write our constraints just once, and then if we need something like a solidity verifier or a Groth16 verifier, we can evaluate constraints symbolically, get essentially an AST of constraints, and compile that to solidity or whatever format we need. And it's also just a more flexible toolkit for building polynomial ILPs. So whereas Plonky2 was very focused on a particular set of choices like the Goldilocks field, Poseidon hash, and so forth, Plonky3 has a lot more options. It has, for example, the traditional FRI-based PCS, as well as the Circle Stark-based PCS. It has support for different permutations, hashes, vector commitment schemes, and so forth. And also just a lot more options. So now we have currently 5 different field options and 7 hashes. So it's very easy for a project like SP1, for example, to experiment with these different options. For example, something like SP1 could switch from the traditional FRI-based PCS to the circle start-based PCS with just a few lines of configuration, or they could experiment with other hashes, maybe switching from Poseidon 2 to Monolith, or trying out a more conventional hash like Ketchak or Blake. And finally, that brings us to the future directions of Plonky3. There's a few directions that we want to explore here. One is that we want to finish the implementation of this tensor PCS to support things like Ligero, Breakdown, and Orion. And that's partially finished, and we've seen very, very good prover performance with that. We can encode data at a rate of about 1 gigabyte per second on a MacBook Air, which is about 3 times faster than Reed-Solomon encoding. So that's very promising. There is the succinctness concern, but maybe it still makes sense in certain uses. We also think that things like Binius are really interesting as well, although it might not fit quite as well into Plonky3 because Binius just requires a very different approach to constraint programming. And we're also looking at things like folding schemes and GKR lookup to support in the future. And finally, there's a lot of work on optimizations. A few of our teammates were here in New York this week just working on things like FFT speedups and faster hashing. Thanks very much, and I'd be happy to take any questions.
Great talk, Daniel. You commented at the beginning that you see M31 as the endgame for CPU-based provers. Do you have thoughts on comparing Baby Bay and M31 on GPU-based provers?
Yeah. On GPU-based provers, so just to repeat the question, I think it was about maybe what's the ideal field or how these fields compare on GPUs rather than CPUs. So yeah, I think on CPUs, M31 is sort of the clear winner, except maybe for certain binary fields, like the AES field, since that has some native CPU support. But yeah, on GPUs, I think it gets a little bit more murky since like the things like shift instructions versus multiplication instructions don't have such a clear difference on the GPU side. But I'm not really an expert on that. But yeah, I do think it is true that like this idea that Mersenne fields are superior is somewhat specific to CPUs, and at least if we think about custom hardware, it seems like binary fields or maybe just comparing like Mersenne fields to some kind of Salinas type prime, there might not be such a big difference in hardware because we can do like a Crandall style reduction or something like that pretty quickly.
Thank you.
Mm-hmm.
Hi, Daniel. It was a great talk. And I'm just curious, you didn't mention much about recursiveness regarding proofs, and how is Plonky3 doing with it, and then what's his plan?
Yeah, a great question. So recursion in Plonky3. So in Plonky2, we had really one set of recursion gadgets that was built in and kind of used almost universally. In Plonky3, we're sort of being less opinionated on this, and we don't really have a native recursion solution that's built in. At the moment, there's a couple ways of doing recursion that were both driven by Nexus Labs. So first, they were trying doing recursion on SP1, which would be a very nice solution because, in theory, we can take the Rust verifier, compile that to SP1, and run that without any kind of custom work or with minimal acceleration. But they found that it didn't work that well in practice, and now they're moving to a custom ZKVM that's specifically designed for recursion, kind of along the lines of what RISC-0 is doing there. So yeah, I think that's what we have at the moment. I think in the future there might be other options, like something based on Velita or other ZK-VMs. And we're also thinking about potentially taking the Plonky2 gadgetry and porting that over. Although I kind of don't want to, because it's you know, with these Plonk circuit-based recursion, it's just very hard to do dynamic things. Like if we're starting with a variable length Stark and need to get a single circuit to verify different lengths of possible Starks.
Thank you.
Yeah, thanks. Okay, thank you very much.